Hello. This is Noah Wistman with another recording for an asynchronous statistics class. In this case, we're going to be discussing a topic called statistical equation construction, or the construction of statistical equations. And we'll also be discussing least squares estimates. This particular lecture will work very similarly to the last asynchronous lecture that I posted, in that it will be kind of me discussing the topic in this video. And at several points, there will be moments where I ask you to pause the video and complete some kind of activity where you write about your responses to the material that's being presented. And you will complete these writings for credit for the class. Okay. The goal of this class, just to give a little bit of context, is to continue to set up our transition from descriptive statistics into inferential statistics. Last class we talked about the sampling distribution of the sample mean. In this class we're going to continue to talk about these kind of overarching topics that are relevant to inferential statistics. And we're going to talk about topics that are going to help us transition into learning about the first inferential statistical test that we're going to learn about, which is going to be linear regression. Okay, so that's what's coming up next class. That's what's coming up in the near future. But today, the main topic is going to be statistical equation or test construction, or the construction of statistical equations. And this is a topic that tends to be included in other introduction to statistics type courses that you might take somewhere else, but it's often sort of glossed over, or it's covered very briefly, or it's kind of woven into the teaching of each specific statistical test. What I wanted to do in this course is to take a full lesson, a full lecture to kind of focus on this topic on its own before we jump into the specific tests. That way we can have a general idea of how statistical tests are conceived of before we start learning about each individual test, which are kind of different expressions of that general idea. Okay. So this is going to be kind of the main subject we talk about today. However, we are also going to kind of briefly, towards the end of the class, talk about something called least squares estimates, or least squares estimation. And this is another topic that's similar to statistical equation construction, gets brought up in other statistics classes, but doesn't always get its whole own section. And that's what we're going to try to give it today, so that as we start to learn about specific statistical tests, inferential statistical tests, we have an idea of the framework or the big picture that they fit into, the trends, the patterns, the tendencies that are true of all statistical tests, not just the ones that we're learning about. Okay. One of the things that we're going to be doing quite a lot of today specifically, and we'll be doing this a little bit more later as well, but today specifically we're going to be glossing over fancy math stuff. One of the things that is true of a lot of branches of mathematics is that the explanations for why we're doing things and how exactly the things that we're doing are working tends to be very detailed, very involved, very fancy, very rigorous. Mathematicians care a lot about very precisely and deeply and completely justifying the decisions that they're making and the formulas that they're creating. We're not going to dive that deeply into those weeds. If you want to learn more about that stuff, by all means, take a statistics class that is more focused on that content. We're going to kind of, you know, work around those things, describe them vaguely but not specifically, because what we really want to do is get the essential idea of what's going on. We want to know more about what we're doing, more than the justification of why we're doing it. I personally think that the justification of why we're doing what we're doing is very interesting. I'm sort of a bit of a mathematician myself, a fan of math. But it's not necessary to learn about those things if we just want to get a general idea of basically what we're doing. And we can rely on our intuition to tell us that what we're doing just kind of makes sense. What's the full explanation of what we're doing, the full justification of what we're doing? Well, we can learn about that more if we're interested. For the purposes of the class today, we're going to be glossing over a lot of that stuff just to get to the basic idea of what's going on. Okay. So that's our sort of introduction. And with the introduction complete, let me go ahead and introduce our first activity, which is just to write down your thoughts and questions about the topics that I've just discussed. If you have done the readings that are associated with class today, you can go ahead and use those as a basis of some of the thoughts that you have. If you haven't done them yet, you can glance at them quickly now, write thoughts about that, or you can just write questions based on the brief discussion that we've had at this very moment. Okay, go ahead and take a few minutes to write down your thoughts and questions. Pause the video and come back when you're done. Okay, welcome back. Hopefully that went well for you and you had a couple of ideas that you want to write down. Okay, so let's get into the first topic that we're discussing today, which is the construction of statistical equations. Construction of statistical equations. And the goal of discussing this topic is to give us the general form that statistical equations follow and to understand what their goal is, what that form is trying to accomplish. Okay. To understand this, we need to start with a little bit of a recap of the topic that we discussed before, which was the sampling distribution, or sampling distributions. The reason that we need to start with this little recap is because in order to understand the way that statistical equations are constructed, we need to understand kind of the problem that we're trying to solve, or the goal that we have in the construction of these equations. So let me go ahead and recap sort of the issue of samples, populations, and sampling distributions right now. This should all sound familiar to you from the previous class. Okay. So when we do inferential statistics, we have some kind of population that we're interested in, and there's a lot of people, there's a lot of things in this population. We can't get to all of them. And what we do is we take some kind of sample, maybe we take 2 samples, 3 samples, but we take some kind of sample from that population. We get information about this sample. We get the mean, maybe the standard deviation, maybe some other stuff. And we want to use that to make predictions, guesses, statements about the population. This is what we would do in inferential statistics. Now, let's say I take some kind of population whose information I don't know about. I take some kind of sample out of that population. I get these kinds of values in my sample. Let's say I get a mean that equals 5, Let's say I get a standard deviation that equals like 2. Okay, just making it up. Now, does that necessarily mean that the mean of my population is 5 and that the standard deviation is 2? No. It doesn't necessarily mean that. Why is that the case? Well, when I took the sample out of the population, I'm hoping that I got a sample of people or of observations that is similar to the population, but I may not have gotten it. Maybe I just happen to get people who have relatively high measurements, and the real mean of the population is 3, and I just happen to get a group that was all of the really high scorers. Maybe the real mean of the population is something like 7, and I just happen to get all of the low scorers. There's no way for me to know that for sure just looking at this sample. We know this because if we set up a distribution where we already know the answers, remember we did this in our last class, we say I'm just going to make up a population and the mean is going to be 5 and the standard deviation is going to be 2. If we take samples out of this population, we take multiple samples, we'll find that in this one we get a mean of 6 and a standard deviation of 1.5. Maybe in this one we get a mean of 5.2. Oh, this one we got one that was kind of close. Great. And we get a standard deviation, let's just say, of 3. In this one, we get another mean, we get another standard deviation, and so on, etc. Every time we take a sample from the population, we get information that's a little bit different from the real values. That's just because of random variation. Okay. This is the issue of inferential statistics. This is kind of the hurdle we have to overcome, that we end up with these differences, these similarities, but they could just be due to random variation. Okay. Therefore, the goal of statistical equations, is to tell us how confident we should be that a difference we see isn't due to random variation. This is the goal of all statistical equations. Maybe that's a little bit extreme, but pretty much every statistical equation, statistical test, inferential statistical test. They're trying to tell us how confident we should be that a difference we see isn't due to random variation. Okay. As we discussed previously, there's more than one way to express the amount of confidence that we have. We can either do it with a test statistic, which can be something like a t value or an f value, a chi-square value, etc. Or those things can be converted into a p-value, as developed by Ronald Fisher. One way or another, whatever method we use, we can also use a confidence interval, an effect size. There's a lot of approaches. But all of these things are trying to get at this idea here. They're all representations of how confident we should be that a difference that we're seeing isn't due to random variation. Okay. So this is the goal of statistical equations. How are they going to accomplish this goal? Telling us how confident we should be. Well, let's go ahead and look at this writing right here, this is one of the readings that's associated with this class. And this is something that I wrote because I couldn't find another source which really talked about this topic on its own. So I decided to write something for it. And you'll see that this kind of covers the very topic we were just discussing. This idea that statistical equations want to tell us how confident we should be in some difference that we see, some prediction that we're making, etc. The results of our test. Okay. And indeed, a lot of what I'm going to present in this lecture will be similar to what is covered here in this piece of writing, but I'll be giving more examples and doing more demonstrations to augment the content that is covered here in the writing itself. Okay. So if we scroll down a bit in this piece, we'll see here sort of my conception of the general way that statistical tests, statistical equations, try to accomplish the goal of telling us how confident we should be that a difference isn't due to random variation, or prediction is not going to be the result of random variation. The way that most statistical equations are constructed is we put information from our sample, statistics from our sample, descriptive statistics from our sample, that makes us more confident in our prediction, more confident that what we have is not due to random variation. We put that over here, we put it over a dividing line, and then we put stuff that makes us less confident beneath that dividing line. What that means is that as we have more and more stuff that makes us more confident, we'll get a bigger and bigger number up here. And if we have more and more stuff that makes us less confident, we'll get a bigger and bigger number down here. What this is going to do is it's going to give us a ratio of stuff that makes us confident to stuff that makes us less confident. And we're going to end up with a single number that represents how confident we are. The bigger this number is, the bigger that this number will be. The bigger this number is, the smaller this number will be, because we're going to be dividing by a bigger number. Okay. Here, I just put some statistical equations. There's a whole bunch of them. These are some of the ones that are classically introduced early on in Introduction to Statistics courses. Here's one for the test for the population mean, test for the population proportion, difference of two means, mean difference in paired data, etc. A lot of different statistical tests here. Take a look at how all of these tests are set up. We have some kind of thing going on up here. It's over a dividing line, and then we got some kind of thing going down here. It's beneath the dividing line. We see the same thing going on here. We've got something above a dividing line, and we've got something beneath the dividing line. The stuff that's up here makes us more confident that there's a difference. The stuff that's down here makes us less confident that there's a difference. Same thing here. Stuff up here, dividing line, stuff down here. Stuff up here, dividing line, stuff down here. Okay. What is all of this stuff in the that is going above the dividing line, that's going below the dividing line? Well, to answer that question, we'd have to talk about these specific statistical tests, and we will do that for some statistical tests that are upcoming. But for now, we just want to take a look to appreciate that general form that they're all fitting into. And indeed, most statistical equations fit into this general form. Not all of them, but most of them. Okay. Now, again, as I mentioned here in the writing, the exact setup of these equations is where the fancy math explanations come in. Here is the equation or the test for the population proportion. This is what it looks like. And why is it set up like this and not like this? You can see here we've got p hat minus po divided by the square root of po times 1 minus po over n. Again, what do all these words mean? Don't worry too much about it. But why have we set it up like this, where we're square rooting the term down here, as opposed to like this, where we have all the same terms, but we are cube rooting the term that's below the dividing line? Why are we square rooting instead of cube rooting? Why are we square rooting at all? Why don't we just have this here with no square root? Why aren't we dividing by 5? You know, why is it that the equation is set up exactly like this? The answer to that question is because of fancy math reasons and justifications. And they are very fancy, and please don't ask me about them because I probably can't explain them to you, at least not all of them. Too fancy. Okay. The goal of today is to not worry too much about exactly why the equations are being set up like this. Again, very fancy explanation. It's just to discuss the general form of these equations. Stuff that makes us more confident goes up here. Stuff that makes us less confident goes down here. Okay. Now, the specific test that we're going to use to kind of demonstrate the construction of a statistical equation is called the one-sample t-test. Put that down here. We're going to be looking at the one-sample t-test. Now, why are we using the one-sample t-test to demonstrate the construction of a statistical equation as an example of the construction of a statistical equation? Well, the reason is that the one-sample t-test is very simple. It's probably the simplest inferential statistical test. Maybe the one-sample z-test is a little bit simpler, but certainly one of the simplest ones. What this is going to do is it's going to make it easy to see the pattern that applies more broadly to more complicated statistical equations. In the one-sample t-test, we're going to see the way that statistical equations are put together in very simple terms, and we can then say, oh, these same principles that we are seeing here apply to more complicated, more fancy statistical tests. Those tests have a lot more going on, but they're basically doing the same thing as this relatively simple test. Okay. So, this begs the question, well, what is the one-sample t-test? Before we can start talking about its construction, we need to talk a little bit about, what is it in the first place? The one-sample t-test is the test we do if we want to compare our sample to the population. And when I say our sample, we have one sample. So we have some kind of population that we're interested in. We take one sample from that population. And we want to compare just this one sample, the mean, the sample, the standard deviation, other information. We want to just compare it to the population. In other tests, we might take, for example, 2 samples from the population, like this, and we might want to compare them to each other. Or we might take 3 samples from the population, and we might want to compare all 3 of these samples to each other. Okay. We might take a sample from the population, measure it once, then measure it again, and compare these 2 sets of measurements to each other. We might want to take 3 from the population and compare all 3 of these samples to each other, or 3 measurements of the same sample to each other. Okay. These are all things we can do. However, you'll note that the comparisons that we're doing are getting fancier, they're getting more complicated. Whereas the comparison we're doing for the one sample t-test between one sample and the population is relatively straightforward. And because it's straightforward, it's a little easier to talk about and understand how it's being put together. Okay, now, in order to compare this one sample that we have to the population, we need to know information about that population ahead of time. If I have, say, the mean of my sample as 5, and the standard deviation of my sample is 2, and I want to compare it to the population, but I don't know anything about the population, I can't really go through with that comparison. Okay. I just have nothing to, no point of reference. Is my sample different from the population? Is it the same as the population? I don't know. I don't know anything about the population. So the one sample, we can only use the one sample t-test when we already know the mean of the population. Whoops. Sorry about that. We already know the mean of the population. If we know the mean of the population, then we can compare that mean to the mean of our sample, and we can make some kind of statement about that comparison. This is what the one sample t-test does. Specifically, the one sample t-test is asking whether or not there's a difference between the mean of the population and the mean of our sample. Now, as you might imagine, situations where we have the mean of a whole population are relatively rare. It's just not that common for us to know what the mean of a whole population is, and if we knew that, we might not be as interested in studying something like that because we already have the answers. Because of this, the one sample t-test is not used that often in practice, because again, these situations are just kind of rare. But again, we're learning it now, not so much because we need to know about this specific test, but because learning about this test will let us see how other tests that are more complicated are constructed. Has the same principles of construction. Okay. So that's the one sample t-test. That's what it's trying to do. Now, what we want to know is our sample different from the population? If it is different, is that difference due to random variation or a real difference? What do I mean by that? Well, let's say that we go ahead and we go and say that our population is going to be all of the students in the United States. This is students in the US. And we're going to be looking at SAT scores. SAT scores. This is something that we will likely actually have, something that closely resembles a population mean for, because the SAT is tracked very rigorously, it's given to a lot of students, and the mean score from year to year is tracked by the people who operate the SAT. Let's say that the mean SAT score we know from this year is 1,030. It could be 1,029 a given year. Let's say it's 1,030. And what we want to know is we have a class right here, and they've been receiving some kind of special SAT instruction. we want to know, is that SAT instruction working or is it not working? So we look at this class, we find their mean SAT score, that's getting the class that's getting the special instruction, and we find that their mean is 1,037. Okay. And the question we have is the special instruction that we're giving this class working to raise the average SAT score of the students who take the class? Or is it not working? Is it creating a difference, or is it failing to create a difference? Well, on the one hand, I could look at this and say, well, the mean SAT score of this class is higher than the mean SAT score of the students in the population. Therefore, our instruction must be working. It must be raising the average score of the class. But on the other hand, I could say, well, 7 is not really that much higher. 1,037 is not really that much higher than 1,030. So maybe the difference that we found between this class and the population is really just a difference that's due to random variation. We just so happened to get a class that got a slightly higher score. The extra special teaching that we did didn't really do anything. Which one of these is the case? Is it that the intervention actually did something, the special teaching actually did something and raised the average grade? Or is it just that we got a class that happened to do a little bit better? And how confident should we be in either one of those statements? The statement that this is due to random variation versus the statement that this is due to a real difference between the sample and the population. What information from our sample can we use to help us make that judgment call? This is the question of the one sample t-test specifically. Okay. Let's go ahead and go back to the piece of writing here, which talks about the construction of the one sample t-test using this very example of SAT scores of students in our class to the national average. What kind of statistics will we need to make this comparison? Well, one of the things that would stand out to me, that would be my first thought, of something we could look at to see, are our students doing better on average than students in the whole nation, is we would want to look at the mean of our sample and compare it to the mean of the population. This is kind of what we were doing already right here, where we said the mean of the whole population is this, the mean of our sample is this. Let's compare these things to each other and say, are they different or are they similar? The mathematical operation that we do when we want to see how different two things are is, generally speaking, it's subtraction. That tells us difference between things. If I do 10 minus 7, that tells me that the difference between 10 and 7 is 3. As opposed to addition, multiplication, division, they don't really tell us that. This is what subtraction tells us. Okay, well, with that in mind, the first comparison that we would want to make, the first piece of information we would want to look at when we're trying to figure out how confident we should be that this difference is real and not due to random variation, is going to be looking at the mean difference, which goes ahead and takes the mean of our sample and subtracts the mean of the population. Once again, let's say that the mean for the whole country, which is our population, is 1,030, and let's say our class got a 1,062 on average. This would give us a mean difference of 1,062 minus 1,030, the mean from our sample right here, minus the mean from the population right here. That would give us a mean difference of 32. Okay. That's a pretty chunky difference right there. 32 more points on the SAT on average. If we were to look at here, that's definitely a bigger difference than the one that we did in the example here, where our class only got a 1037, only 7 points above average. Okay. Let's go ahead and look at some other examples. Let's say that we looked at other classes that we were teaching, maybe with different methods of instruction, and to see how they were doing. Which result would make you the most confident that there's a significant difference between our class and the national average? Now here I have kind of integrated a bit of statistical terminology into the expression of these questions. The term significant difference or significant change or significantly greater, all of these have a kind of special meaning in statistics, significantly greater, which we talked about in terms of hypothesis testing. And all of these are basically trying to get at how confident we are that there's a real difference. If there's a significant difference, that means that we're very confident that there's a real difference. Okay. Just a bit of terminology, kind of the same idea being expressed differently. Okay, so let's look at these other classes here. Which one would make you the most confident that there's a significant difference between our class and the national average? Which would make you the least confident? Here we have a class that the mean was 1001. We do the mean of the sample minus the mean of the population, and we find that there's a mean difference of negative 29. Okay, let's look at this one. This class had a 1031 mean of our sample minus mean of the population. That's a mean difference of 1. Let's look up here. This class got a 1060. That's a mean difference of 30. So it seems like the larger the mean difference is, the more we can say with some confidence that there's really a difference between our sample and the population. Here, it looks like our students are doing quite a bit worse in this class. The mean of the whole population is 1030. Students in this class are only getting 1001. That's a lot lower than the mean of the entire population. Maybe this class is struggling. Maybe the teacher's not doing a very good job. Maybe the method of instruction isn't really all it's cut up to be. Over here, we have a class that's getting 30 points above the population. This class is doing really well. We might be pretty confident that there's a real thing going on in this class that's making people perform better on the SAT. On the other hand, this class, sure, it's different from the population. 1031 is not exactly the same as 1030, but it's only like a little bit different. This difference could easily be due just to random variation between the different samples that we take from the population. It might be that the professor in this class isn't doing a particularly better or worse job than in the general population. Here we have some kind of in-between options where this one also not a huge difference. I'm not that confident that this isn't just due to random variation. This one I'm definitely feeling a little bit better about. There's a bigger mean difference, but I'm not feeling as good about it as I am about these outcomes. So the larger the distance between the mean of our sample and the mean of the population, the more confident we should be that there's something going on in our sample. And the difference isn't just due to general random variation between samples. Okay. Now, If only it were this easy. If only we could just say, oh, let's just look at the two means, see how different they are. Well, bam, that's all we have to do. Sometimes, though, mean difference isn't the only thing that matters in our assessment of how confident we should be that there's a real difference between our sample and the population. What's something else that matters? Okay. Well, let's say that we broke things down a little bit more. We looked at some more of our classes to get more examples. And we got one class whose scores looked like this: 1041, 1042, 1048, 1040, 1040, 1039, 1043, da 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 da, for a mean of 1040.909. Trust me, I worked it out. And we got another class whose scores looked like this: 1022, 1048, 1064, 1028, 1054, da 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 da, mean 1040.909. Just taking a look at the scores that were obtained in these two classes, which one of these seems like there was more variation in the scores in the class? Well, obviously that would be class G with more variation, and class F with less variation. Here, everyone is getting something between like a 1039 to a 1043. It's all high 1030s to low 1040s. Every single person. A very consistent result from this class. Not a lot of variation in this class. It seems like the teacher in this class got everybody sort of up to the same level, let's say. Whereas in this class, the scores are kind of all over the place. We got this person with a 1022, this person scoring poorly with a 1008, this person scoring super high with a 1064. In this class, it seems like there's more just variation between the scores that people are getting. Now, the mean of both of these classes works out to be exactly the same. You can double check it yourself, or you can trust that I did my calculations correctly. Which begs the question, which class would have a higher standard deviation? And which class's result would make you more confident that there was a significant difference from the population and not one that's due to random variation? Well, I think class G would definitely have a higher standard deviation. Its scores are more deviating from each other, whereas here they're all bunched up around the same general results. And this one would definitely make me think like, hey, there's more random variation going on here than there is in this one. So I would probably be more confident that there's a real difference from the population, where again the mean is 1030, in this group than in this group, even though they have exactly the same mean. There's just more variation going on in this one. And indeed, a higher standard deviation makes us less confident that our result isn't the result of random variation. More variation seems like we can be less confident that a result isn't because of random variation. Therefore, we would want to include standard deviation in our equation so it makes our final number smaller. If we go up here, if you remember, in our general construction of a statistical equation, we want to put stuff that makes us more confident on top and stuff that makes us less confident on the bottom. Standard deviation, a higher standard deviation, makes us less confident, so we would want to put it on the bottom of our equation. We can do this by dividing the mean difference by the standard deviation, just like this. Here we have the mean difference, of which a larger mean difference makes us more confident on top. And here we have the standard deviation. A larger standard deviation makes us less confident, so it goes on the bottom. This way, the larger that our mean difference is, the bigger our number will get. The larger the standard deviation is, the smaller our final number will be. Okay, let's keep going. Because we're not quite done yet, we have a lot of the key pieces that we need to make our statistical comparison, but there's still another one that's missing. Let's say there were some classes, again, I'm still looking at my classes and their SAT scores here. I want to see how everyone's doing. Let's say there were some classes I couldn't get everyone's scores from, therefore giving me different sample sizes. Which sample size would make you the most confident in the results that you're looking at? Let's take a look at these classes. Here in this class, class H, I was only able to get the results from 2 students. Maybe there was some kind of clerical error where not everybody's scores were kept track of. This one I was able to get 6 results. This one I was able to get 33 people's results. Which sample size would make you the most confident in the results that you were getting? This tends to be pretty intuitive to people, where it just makes sense that the larger sample that we get, the more confident we can be in the results. Going back over here, let's say that I got a sample from the population. We're looking at SAT scores, and I found that this sample had a mean of like 1,078. Now I could look at that and be like, wow, that's a pretty big difference from the mean in the population. It seems like the students in this sample are really doing a lot better than students in general. But then let's say I told you that the sample size, represented by n, was 2. And that this mean was based on the scores of exactly 2 students from the class. Now all of a sudden, my result doesn't seem very impressive. It seems like, you just got 2 people. It's entirely possible you just happened to get the 2 good students who did well on the SATs. You would look at me and be like, go back and get more people. What are you trying to tell me over here? I'm not going to be convinced by the results of 2 people from the class. Now, let's say that I was like, oh, I'm sorry. I went back, I got more people. Now I got the results of 30 people, and the mean is still, in fact, 1,078. Okay, now maybe you feel a little bit better. You didn't just go look at 2 people, you actually went and you looked at 30 people. That's a little bit more substantial. Maybe you feel like, hey, this number is still a little bit small, 30, I don't know if that's really enough. Go use the same teaching method you're using in this class, get me 300 people. Okay, now I feel a lot better. That's a nice big sample. I can be confident in the results that it's getting. Okay. So a larger sample will pretty much always make us more confident in our results because we just get more information with a larger sample. Now, how are we going to include this into our equation? Well, let's go ahead and take the mean difference on top, the standard deviation below that, and let's put the sample size underneath the standard deviation so that we're dividing the standard deviation by the sample size. This way, the larger our sample is, the more it will reduce the standard deviation, and the larger our final number will be. We can look at a few examples of this. Let's go over here. So the way we've set this up is that we have the mean of our sample minus the mean of the population divided by the standard deviation, which is divided by the sample size. Let's make up a couple of numbers here. The mean of our sample is 3. The mean of the population is let's make the numbers easy to work with. Let's say that the mean of our sample is 6. The mean of the population is 3. The standard deviation, let me do an even number. Let's say that it is 2. The standard deviation is 2. And the sample size is 10. Okay. This would give us 6 minus 2 is 4, divided by 2, divided by 10, which is going to give us 2 divided by 10. It's going to give us 0.2. Great. This is going to give us 4 divided by 0.2, which is going to multiply it. We'll do that on our calculators. Pull one out right now. 4 divided by 2 divided by 10. Again, this is important here. Bam. 4 divided by 2 divided by 10 is going to equal 20. Very big, very nice big number here. Now let's say that instead of a sample size of 10, we got all the same information, but we got a sample size of 100. Okay, let's go ahead and look at that. We do like this and like this. Remember, these are on above and below the dividing line. Okay. Well, you plug that into your calculator, you get 4 divided by 2 divided by 100, and we're going to get 200. You can see that increasing our sample size from 10 to 100 made our number that represents how confident we are much bigger. We could do similar things by trying different mean differences out, seeing does a bigger or smaller mean difference do anything, and trying different standard deviations out, seeing does a bigger or smaller standard deviation do anything to our final confidence number. And hopefully, if we've set up the equation well, the bigger our sample size and our mean difference are, the bigger this number will be, and the bigger our standard deviation is, the smaller this number will be. Okay. Now, let's compare the equation that we just put together here with the official equation for the one sample t-test, shown over here on the right. We've been talking about things like, hey, here's our number that shows how confident we are. It's equal to the mean of the sample minus the mean of the population divided by the standard deviation divided by the sample size. Well, here's the official equation for the one sample t-test, where t is equal to the mean of the sample minus the mean of the population divided by the standard deviation divided by the square root of the sample size. Okay. You can see that the equation we put together is almost the same as the official equation. In this case, rather than saying, the confidence number, we're saying t, which, as I mentioned before, is one of the results of a statistical test that represents how confident we are. In this case, we're doing the one sample t-test, so we get a t-value. And the only other difference is that we are dividing the standard deviation by the square root of n, rather than just dividing by the sample size, n. This is where the fancy math comes in. Why are we square rooting the sample size instead of just leaving it as it is? Well, that's because of fancy math reasons, which have to do with how much information we're getting from each person in our sample. You can ask me about this sort of after class if you're interested. You can ask me later on because I think that the full explanation is pretty cool. But we don't need to worry too much about the full explanation because despite the differences, you can see that the basic setup is the same in terms of things that are more confident, making the number bigger, things that make us more confident, making the number bigger, things that make us less confident, making the number smaller. Okay. A lot of equations follow the same basic form. The one sample t-test uses the mean and the standard deviation in order to do our comparison. Other tests use other kinds of information. We'll learn about those kinds of tests when we talk about the chi-square goodness of fit and the chi-square test of independence. But a lot of the tests that are popular, that are commonly used, specifically use the mean and the standard deviation as their points of comparison. Okay, but we'll talk about some of those other tests as well a little bit later. But all of them fit into this general sort of setup where stuff that makes us more confident divided by stuff that makes us less confident. Okay. At the end of this writing, I've thrown on the sort of short formal mathematical proof for the one sample t-test. I can't tell you what all of this stuff means, especially the stuff down here. I get a little bit lost. All of this is to show that there's a lot of fancy math going on behind the argument that we just made. But we don't have to understand all of this fancy math to understand basically what we're doing when we're looking at the official test for the one sample t-test. Okay. The main takeaway being that statistical tests aren't just random assortment of symbols. They are mathematical expressions of comparisons we want to make. Specifically, they're expressions that are trying to tell us how confident we should be. That's kind of the takeaway I want you to have from this section, from this topic. Okay. This brings us into our next activities here. Sorry, I've been talking for a little while, but it's time to pause. For activity number 2, what I want you to do is take the equation for the one sample t-test, which again, let me demonstrate that real quickly. You can pause the video to look at it here. You can also look this up. It's available in plenty of places. It's the mean of the sample minus the mean of the population divided by the standard deviation divided by the square root of n. Go ahead and take that equation. Try plugging in some numbers and changing them. Try different mean differences, standard deviations, and sample sizes. You can do this on your calculator and just sort of see what happens note the results. So on the worksheet, you should just kind of write what numbers you put in and what the t value was. And just look at, maybe take a few notes on, what is happening when this number is bigger and this number is smaller versus when this number is bigger and this number is smaller. Okay, go ahead and pause the video and try plugging in those numbers just for a little bit. Get a sense of what happens when they go up and down. Take a few minutes to do that. Okay, welcome back. Hopefully you got a feeling for what this equation is doing, and hopefully you understand kind of why it's doing it, what the point of setting things up this way is. This is going to bring us to our next activity here, activity 3. We're doing 2 activities based on the presentation I just gave. In this next activity, go ahead and write the one sample t-test equation and annotate it. What do I mean by that? Let me demonstrate here. I'll go ahead and make some space for myself. Sorry, recap. Okay. So what you're going to do is you're just going to write, and you can do this by hand or you can do this on the computer, whatever way works for you. You're going to write the equation for the one sample t-test. And what I want you to do is just to kind of go through the equation and label what everything is. So this here we know is the population mean. Okay. What is this thing right here? Well, this is the sample mean. Okay, we're just labeling things. And we can label this as the standard deviation, this is the sample size. Okay, then I want you to maybe add a couple of more notes and be like, okay, the population mean, we need to know this ahead of time. Often we don't, so the one sample t-test is rare. Okay. So what we're doing is we're just looking at the different aspects of the equation and we're labeling them. We're kind of annotating them. Maybe I can sort of circle this here and say that whole thing together is called the mean difference. That's what this is here. How different the mean of the sample and the population are. Again, this is the idea of annotating the equation. Okay, maybe I want to go here and say this right here, this is the square root. And I can say we do for fancy math reasons. Square root of the sample size. Okay. So this is what I mean when I say I want you to annotate the equation. You can go ahead and use some of the annotations I've done here, add some more of your own, phrase things in your own words. We're just going to try to break down the equation, label the parts, describe those labels so that we remember how the equation is set up and a little bit of why it's set up that way. Okay, so go ahead and write the one sample t-test equation and add some of your own annotations to it, phrase things in your own words. Pause the video, take a little bit of time to do that. Okay, welcome back. Hopefully that went well for you. I will mention right now that this way of studying equations and mathematical formulas and mathematical tests, this sort of annotation approach is something that I really recommend in general. If you take other math classes, you can use a similar strategy to help you understand and remember different equations and mathematical concepts. Okay, we'll probably be doing similar things with some of the other statistical tests that we learn about. Okay, so this concludes the portion of the lecture that is about the construction of statistical equations. Hopefully you're able to follow it and understand what I'm getting at here. We're now going to just quickly, we're not going to spend too much time on it, talk about least squares estimates and least squares estimation. And the reason we're talking about this is because the next class we're doing is going to be linear regression. It's going to be about regression and linear regression. And regression and linear regression are sort of built on least squares estimates. So we're going to introduce this now to set ourselves up for success when we talk about it a little bit more specifically. Okay, let me go ahead and make a new thing here. I don't need to save this. Okay. Now, what is a least squares estimate? In general, I think the best way to introduce the idea of a least squares estimate is just to show it visually. And we can, talk a little bit more about the details behind it when we talk about linear regression. The best way to show the idea of least squares estimates visually is with a scatter plot. So let's go ahead and make a scatter plot. I'm just going to make a plot here, and I'm going to add some points to the plot. Okay, let's say that my points are kind of distributed like this. Now, one of the ways we might try to describe what's happening in our data here we go and have our y variable and our x variable, is we might say that the data is kind of going up, like this. As y is increasing, x is also increasing. We talked about this when we talked about covariance. Okay, well, let's say that I wanted to be a little more precise in my description other than they both go up. And I wanted to make a prediction about where data points are going to show up for a value of x depending on a value of y. Well, one thing that I might want to do is I might want to try to draw a line that kind of goes through the middle of all of my data points. And what I would say is, look, the data that we have is tending to follow this line. Okay, a little preview of linear regression here. Now, the question that I have is, where should I draw this line? Should I draw the line like this? Should I draw the line like this? It seems like I should draw the line somewhere more like this, like those last two lines were kind of silly, but should it be here, or should it be like here, or should it be like here? Should it be more like this? Like, where exactly should this line go? How exactly should it be set up? And one of the ways that we can try to answer this question is by looking at the distance of our data points to the line like this, and we're trying to minimize those distances, like this. And if we can minimize the distance from the data points to the line, this would definitely give us a line that feels like it's right in the middle of our data points. Now, if you remember way back when we talked about standard deviation, we talked about how to calculate the standard deviation. We can't just subtract every data point from the mean. So whatever point of data that we have minus the mean, so our x value minus the mean. If we do that for all of our x values, when we add that number up, it's going to add to 0, because just as many of them are going to be above the mean as are going to be below the mean. You add them all up, they're going to cancel out. So what we had to do was we had to square all of these values, x minus the mean squared. Let me write that in a better place. We had to do the x minus the mean square. This was the squared differences. And then we had to add them all up, and this gave us the sum of the squared differences, the sum of squares. Little standard deviation recap here. Well, we have to do a very similar thing, and in fact it's kind of exactly the same thing. We'll talk about that. When we want to sum up these distances to the line. If our line is truly in the middle of all of our points, then just as many of them will be below that line as will be above that line. So what we actually have to do is we have to square these distances, add up the squared values of those distances, and this will give us a value that puts our line right in the middle. And we're trying to make this number, the sum of the squared differences, as small as possible. This is our goal, is to put the line right in the middle so that the sum of the squared distances from the line are as small as possible. And this is where the term least squares estimate comes in, where we're taking the distances from points to the line, we're squaring them, and we are trying to make that number as small as possible. Okay, this is also called, we're trying to minimize the sum of the squared residuals, where the residuals are the distances between the points in the line, and we square those residuals and we add them, and we are trying to minimize the sum of those squared residuals. Okay, least squares estimates are all built around this idea. Now, there's more than one way to estimate the distance to a line. Let me draw some more points right here. Draw a line through them. There's actually more than one way to try to estimate the distance between points in a line. Let me draw a good line here. One of the ways we can do it is to go from the point straight down to the line, which is kind of what we showed over here. When we do this, we go straight from the point to the line, straight down. We are calculating what's called an ordinary least square. Ordinary. But that's not the only way we can do things. We could also try to go to a kind of perpendicular angle to make a right angle here. And we could look at this distance between the point and the line. We could also track the grid of the number plane, only go on the integers, and say we're actually going to go like this to the line. This is called the Manhattan distance. In this course, we're only going to look at statistical approaches that look at this kind of distance, the ordinary least squares distance to the line. And that's because these are the easiest to work with mathematically. They're also the oldest approaches. This is how it used to be the only way to do things way back in the day. But just know that there are these other approaches that are out there, and there are statistical tests that are associated with those approaches. Okay, the other wrinkle we can add in here is we've been looking at data where a straight line seems like it's doing a pretty good job of looking at the relationship. But let's say that I had data that was distributed more like this. Here you can see that a straight line is not going to do a very good job of describing what this data is doing, no matter how we draw it. In this case, we might want to draw a line that does something like this. Has the same kind of arc that the data has, and then we could do the same thing we were doing before, where we look at the distances of our data points to the line, and we square those distances, and we sum them, and we try to minimize those squared distances, like this. In this case, we wouldn't be doing a linear regression. We would be doing a different kind of regression that does this kind of thing. We're still minimizing the sum of the squared residuals, but we're doing it with like a curvy, weird line. And indeed, let's say we had an even weirder distribution that was like, wow, and then it goes down, and then it like goes up again. You know, this is kind of how our data is distributed. Well, now we need a line that does something like this. Wow. And once again, we could try to find the sum of the squared distances between the points in the line. Okay. These situations are all associated with different kinds of regression. Okay. Ones where the data is like a straight line, ones where it's like a curvy thing, one where it's doing like this, and ones where we measure the distance straight down versus when we look at it as a perpendicular line. In this course, we're going to learn about the one where things are going in kind of a straight line, and we're going to accept that we would be doing a similar kind of thing with slightly differently if we were looking at these other cases. Okay, again, we'll learn more about everything I just talked about here when we learn about regression in the next class, but this is giving you just a general idea of what we're doing when we do regression, what we're trying to do when we do a regression analysis. We're trying to minimize the sum of the squared residuals, the distance from the points to the line. Okay. This brings us to our last activity. What I want you to do is draw 3 scatter plots, as we've been doing for several previous classes, and draw the line you think would minimize, or do a pretty good job of minimizing, the distance from the points to the line. More specifically, the sum of the squared distances, or the sum of the squared residuals. Okay. Make sure you label your axes with variables that you think would create this distribution. So just to give an example, and you can reuse this example if you like as one of your graphs. Let's say I was looking at something like height, and we've looked at this before, height and weight. Okay. Now I would expect people's height, as people's height goes up, that their weight would also probably go up. Again, this is something we've talked about before. So I'm just going to make a scatter plot like this. But the added wrinkle that we're doing is we're going to draw a line that we think is sort of in the middle of these data points that is going to minimize the distance between the points and the line. Like this. Okay, so I want you to draw 3 graphs that look something like this. Try to draw at least one graph that has this kind of linear relationship, but try to draw another one that has some sort of weirder relationship. For example, I might have something like learning speed and age. And what I might see if I did something like that is that when people are babies, they learn things kind of slowly because they're just trying to figure things out. That improves until they get to be sort of teenagers. And then when they become an adult, it sort of levels out. And then as they start to get older, it starts to go down as they get a little bit slower in their old age. Here, the line that would minimize the distance between the points would probably look something like this. Okay. So this is what I mean when I say that I want you to draw 3 scatter plots, draw the line that you think would minimize the distance from the points to the line, label your axes with variables you think would create this distribution. Okay. Long explanation there, but go ahead, pause the video, take a little bit of time, draw what you feel like the best fit line would be for your 3 scatter plots. Okay, welcome back. So there you go. Those are the topics that we were discussing in this lecture. Again, we talked about the construction of statistical equations up here, and then we had a little introduction to least squares estimates, which we'll talk more about when we talk about regression and the other tests which rely on least squares estimates. Okay, see you next class.